welcome to Tech to Tech presented by KaiZen, where we will explore common cleaning questions and answers. Let's get started. I would like to introduce KaiZen's own Haley Reid.
Thanks, William. Today in our Tech to Tech, we are going to talk about SEM and EDS. We're just going to do a basic introduction to it. What we're going to go over is what SEM and EDS is, what the different detector types are, and how you can use it in your cleaning process application. So, SEM, which everyone's heard of, actually stands for scanning electron microscope, or if you're talking about the method, it's microscopy. This just uses an electron beam that is focused onto a sample and then scanned over the sample in a square pattern to get information. The signals from this electron beam, it actually excites different electrons and photons and can produce topography and compositional information of the surface. The image over here on the right is actually going to show how deep into this sample we're gathering information from. There's a bunch of information that's excited and given out, and depending on how deep in the sample it is what kind of information you have. So the two most common types of SEM data are actually gathered by the two most common detectors, which are secondary electron, SE, or backscatter electron, which is BSE. Secondary electron is actually a topography method. It actually is just showing you surface changes between 0 and 2 nanometers deep into the surface. So it's very sensitive to what this surface looks like. Over here on the right, you're going to see actually high and low points in that top image, as well as like grains of sand sprinkled on it. This is a great method to look at just what your surface looks like and what your sample looks like. The backscatter electron image is really sensitive to the atomic number of what you're looking at. So if you're looking at a very heavy or a very heavy element versus a very light one, you're going to be able to see a contrast of light and dark. The higher an atomic number is for an element, the actual brighter that image is going to be. So something like lead is bright white whenever it's next to something like carbon. This is a little bit deeper into the sample between 0 and 50 nanometers. And if you look on the right, instead of a nice kind of realistic picture like that top secondary electron image, it's very light and dark. There's a lot of contrast in all backscatter images, and this is because it's looking for different atomic numbers. Now, 0 to 50 nanometers seems like it's pretty deep into the surface, but for reference, we're going to have a strand of DNA being 2.5 nanometers wide, or your fingernail growing about 1 nanometer a second. I think it's actually zero point 0.9. And a piece of paper is around 75,000 nanometers. So we're going into the surface, and this does matter for really thin stains, but we're not going into the surface very much. The third most common type of detector is actually EDS or EDX or EDAX, which all stand for energy dispersive X-ray spectroscopy. It's got a bunch of different names based on the original detector that was made or where you're at in the world. If you're over in Europe, it is going to be EDX. This method actually is to determine the composition of a sample, and you're going to get weight percent numbers back generally. So you'll get a spectra, you can have weight percent numbers, and these are all semi-quantitative, which just means whatever percentage you get back. So if you get back 1 to 2% of oxygen, it will actually be 2% oxygen plus or minus 1%, depending on your calibration. It's also important to note that the atomic number of the element that you are looking at generally needs to be above 10. Oxygen is less, carbon is less, and we can detect those, but not with a lot of accuracy. Where once you get to heavier metals, we're a lot more confident in how much is there. The penetration depth for this method is actually 500 nanometers, which is quite a bit more into the surface than the other two, where SE is 0 to 2 and backscatter is around 50. So this is 10 orders of magnitude deeper. So just to think about that whenever you're looking at a stain, it's very possible to go past it. The image on the right, you can actually see a spectra from EDS, where the main component in this one was aluminum, and you can just see a peak like you would for GC or IC or any of those other spectroscopy methods. Using SEM and EDS in your cleaning process, we actually use this generally in four main ways. The first one is metal compatibility of your cleaning chemical or any other compounds you're putting in, like buffing compounds or anything like that, epoxies. You can identify remaining flux residues or any other type of material remaining on the surface. You can characterize surface changes. A lot of times, like surface roughening or staining can be seen. And you can also do element identification, assuming that you have 500 nanometers of material. Over here on the right, you can actually see two solder bumps that have a dendrite growing between them, and you can see that bridging very clearly using this method. So the most common way we use SEM is metal compatibility. On the left, you can see a solder bump before cleaning surrounded by flux, which is denoted by the dark ring around it since we're in backscatter. But the actual solder bump is very smooth, just some outgassing holes, but that's very normal. On the right side, we can see the solder bump after cleaning. There's no flux surrounding it, so we've cleaned it, but the solder bump is now rough. The holes are much larger, and the solder bump itself is much smaller. So this cleaning chemical was incompatible with the bump, but it did clean it. So we'll keep looking for something there. We can also use EDS for metal compatibility. We most often do this whenever we're using flip chip applications. Everything is so small, it's quite hard to see with any other method. But with this, we saw on the left before, you can see aluminum surrounding the SAC 305 bump. There's the red is aluminum where the green is silicon because it's actually a silicon wafer underneath. On the right side, after cleaning, you can see that there is some aluminum on the surface, but mostly that pad is now silicon. That means we actually lifted the aluminum off, leaving just the silicon pad behind. So this was a great method that we couldn't use normal microscopy for this, but this made it very clear this was incompatible. We also use SEM for remaining residues. We here have flux on the left and buffing compounds on the right. For the flux residue, you can see the solder bump on top there, surrounded by that dark ring of flux. We actually just cleaned this with water just to show that it wasn't cleaning, but you can see how much flux is there versus the bump. That's very easy to see. And on the right side, you can see the clean surface with two residues on them, two big blobs, which actually ended up being buffing compound on this surface, but it just looked like black specks visually. So putting in an SEM, we could identify what it was and the cause of it, and we were able to remedy this. We can also use SEM for surface changes. So before you can see a solid surface that's one color, it was a little bit darker because it needed to be cleaned. On the right, you can actually see a light and dark change in this surface. Visually, this looked like a white band on this brass surface, and we were trying to identify what it was. But this was too thin for us to see in EDS because it needed to be about 500 nanometers thick. And we need to keep that in mind anytime we're looking at surface changes like this. The characteristic X-rays, which are what EDS uses, are 500 nanometers deep into the surface. So we couldn't use EDS to determine the nature of this stain. We were able to fix it, but we couldn't find out exactly what caused it originally. You can use EDS for some surface changes. Like here, we had a part that, after cleaning, had dark splotches all over the metal. And no matter how much we cleaned it, it stayed. So we ran EDS on it, and you can actually see using this bright yellow in the left bottom corner that there was nickel being plated back onto the surface, and that was causing that discoloration there. This was actually a process issue, not a cleaning issue. It was just revealed after removing all the contaminants from the surface. Okay. So, frequently asked questions about SEM and EDS. Number one, can we use SEM or SEM EDS to identify a stain or discoloration? This often comes in metal parts. Hey, my part is too dark. There's a blue hue, there's a yellow hue, any of that. And we can sometimes. We can use SEM to determine if a surface was roughened, which it can cause a different appearance, or if there was any pitting or anything like that, which would cause a different color. And SEM EDS is great if there's a lot of something present. So sometimes we can see something wasn't cleaned all the way off, like flux residues, and that's a great way to identify a stain. It just has to be 500 nanometers thick. Second question, what size parts do, do we need to be inspected with the SEM? So SEM actually has a chamber that's pulled under a vacuum, and so you need a little bit of a smaller part. It needs to be 15 millimeters, not nanometers high, and it needs to have a flat or as flat of surface as possible. And the actual like size, it needs to fit on a 120 millimeter diameter circle. So if you're sending a part in, it will probably need to be cut up to be fit in a SEM. Can SEM or EDS detect plating issues on metal parts? Absolutely, it can. We use this method for this a lot in detecting plating issues, whether it's plating that's inconsistent across the surface, or there's big holes in plating, or pitting. This is a great method for this. SEM can tell it a lot of time just using backscatter and that elemental composition difference, where EDS can tell us what metals are being improperly plated. So this is a great method for that. The fourth question is, should I use FTIR or SEM EDS for my application? Which one's better? It depends what you are looking at. Both do better on a metal surface or something you can scrape off. Both penetrate 500 nanometers or more into the surface. FTIR actually penetrates, I think it's like 650 nanometers or a little more into the surface. So it's a little bit deeper of a method than SEM EDS. But FTIR can actually use the chemical bond or the bonds to tell you what that chemical is. So it can tell you if it is an epoxy or if it's a silicone or something like that. It's actually going to be able to match that with a percentage. So it's 99% match to your epoxy. SEM EDS is better for metal type stains and identification. And also, it can tell you if there's carbon there or if there's oxygen there, and it can tell you a percentage ratio, where FTIR doesn't usually do that. It just gives you a spectrum. So it depends on your application. If you want to know exactly what it is, FTIR. If you want to know what elements are there, SEM. The final question is, how long does it take to complete an SEM scan or an SEM EDS? Preparing the sample is generally the longest portion of it, and this can be up to an hour depending on if we need to polish something, if we need to cut it down, how we need to treat that surface. Once it's actually in the machine and the machine is down to the correct vacuum, SEM scans only take 1 minute. From the top of the image to the bottom, it's a 1 minute scan of a very tiny portion of your part. SEM EDS, if we wanted to get a very pretty picture and a map like we've seen in this presentation, that's usually going to take an hour or more because you want multiple scans of that to tell you to get a good picture. Where if you're just doing a quick scan to say, hey, what elements here, what elements not, it's a 1 minute scan and it's a very quick scan. That's all for my presentation. Back to you, William.
Thanks, Haley. And thank you all for watching this Tech to Tech session. If you would like to discuss this topic further or have any questions not answered in the session, please contact your local Kaizen regional manager or send an email to tech, the number two, tech kaizen.com, and we will have someone follow up with you as soon as possible. Do you want to have exclusive access to future content sent directly to your inbox, or do you know someone who would benefit from these sessions? If the answer is yes, just go to tech by kaizen.com and fill out the subscription form. And if you like this video, be sure to follow us on our social media platforms for more expert cleaning content.